A smooth particle of mass 3 kilograms is attached by a light inelastic string to a point P. The particle describes a horizontal circle of radius 0.5 meters on the smooth surface of a horizontal table. The center of the circle is vertically below P. The string makes an angle alpha with the vertical, where tan of alpha is 4/3. The speed of the particle is 2 meters per second. We are going to get the tension in the string. Let's start by looking at the forces on this particle. Well, we obviously have its weight, which is vertically down. It's m times g, where the mass is 3. So this vector has magnitude 3g. Now, since the particle is attached to this string, we have a force on the particle in a direction along the string. We will call this force T. Now the particle is in contact with this surface, so there is a force on the particle due to the surface, a contact force, and that's in a direction perpendicular to the surface of contact. So that's going to be in a direction that's perpendicular to the table. So I will call this force N. Now the particle is moving along this circle. The table is smooth, so there are no forces opposing the motion of the particle. No friction forces, in other words. Now let's suppose that the particle is moving with constant or uniform speed on the circle. We're given that the speed at this instant is 2 meters per second. I'm trying to show this velocity vector. It's going to be in the plane of the table, okay, tangential to the circle at this point, and its magnitude is going to be 2. Anyway, we know from previous videos that for uniform circular motion, the resultant force vector always points towards the center of the circle. So the resultant force vector is constantly changing direction. When the particle is here, the resultant force vector will be in this direction, So it's constantly changing direction, but its magnitude is constant. Its magnitude is mv squared divided by r. Let's get its magnitude. So m is 3, the speed is 2, and the radius of the circle is 0.5. So if we work this out, we have 3 times 4 is 12, divided by 0.5 is 24, and this is in newtons. Now notice that it didn't specifically say in this question, or state in this question, that we are dealing with uniform circular motion. It just says the speed of the particle is 2 meters per second. Okay, so it could be just 2 meters per second at this instant. The particle could actually be speeding up. So is our approach going to apply in that case? Well, actually it is. I've explained this in detail in other videos, and I said that if the particle is speeding up, the resultant force vector at any instant is not pointing towards the center of the circle. So if the particle is moving, say, in this direction, the resultant force vector will be pointing off here somewhere if the particle was speeding up as it's moving anti-clockwise around the circle. But what I did say in those videos is that the component of the resultant force in that case still has magnitude mv squared over r. If we take the component of the resultant force along this radius line, this magnitude is given by this, so we can still work with this even if we are not dealing with uniform circular motion. Okay. Anyway, that's just an aside. We don't have to worry too much about that. We can just assume that in all these problems we are dealing with uniform circular motion, unless of course we have a vertical circle with an object rolling down the circle where the object is speeding up. For horizontal circular problems we have uniform or constant speed. Okay, let's write down a vector equation for the forces acting on the particle. So the sum of the forces acting on the particle must equal the resultant force F. So we know that the horizontal component, the sum of the horizontal components of these 3 vectors will equal the horizontal component of the resultant vector. By horizontal component I mean that at this instant of the particle's motion we're interested in the components along this line here, the radius line. So let's get the horizontal component of vector t. Well, if we were to project the tip of vector t down onto this line, we would see that the horizontal component of vector t lies along the radius line, points towards the center of the circle. So one way to get that vector would be to show it up here. Okay, here's the horizontal component of vector t. It's part of a right angled triangle. Now this angle in here is alpha, the same as this angle. We have a pair of z angles here because vector n is parallel to this dotted line here, since vector n is perpendicular to the surface of the table. So I'll show this triangle out here. Well, I'll not necessarily this triangle, but a triangle that's similar to it. We're given that the tan of angle alpha is 4/3. So we could show angle alpha in a right angle triangle, make the side opposite angle alpha 4, make the side adjacent to angle alpha 3. So this triangle is similar to this one here, but not necessarily the same as it. The sides could be different. Okay, so how do we get this side here? Well, this side of the triangle is opposite angle alpha, so we have to multiply the magnitude of vector t by the sine of angle alpha. The magnitude of vector t is just t, so we multiply t by the sine of alpha to get the side opposite alpha in this triangle. That's going to be the horizontal component of vector t. Okay, what about the horizontal components of n and 3g? Well, n is perpendicular to the table, so its horizontal component is 0. The horizontal component of the weight vector is also 0. So the sum of the horizontal components of the three forces acting on the object is equal to the horizontal component of the resultant force. So what's the horizontal component of the resultant force? Well, that's just equal to the magnitude of the resultant force itself, because the resultant force is entirely in the horizontal direction. It doesn't have any vertical component. And you can see that it's pointing towards the center. The horizontal component of t points in the same direction as the resultant force F. Okay, so if you want to make it positive, you can. For vectors pointing towards the center, vectors pointing away from the center would be negative. We don't have that here, so this would be plus F. Putting the plus sign to emphasize. But anyway, that's just overdoing it. So this is 24. Now we can find t by getting sine of alpha. Sine of alpha is opposite over hypotenuse. So what's the hypotenuse of this right angle triangle? Well, we can use Pythagoras. 3 squared plus 4 squared is 9 plus 16, 25. Square root of 25 is 5. Sine of alpha is 4/5. Okay, see, if we know tan alpha, we can get sine alpha. And if we work that out, 24 divided by 4 is 6. 5 sixes are 30. So the magnitude of vector t, the tension in the string, is 30 newtons. Now, to get the reaction force between the particle and the table, that's vector n, we notice that the vertical components sum to 0. That's because the particle does not move in the vertical direction. It remains in this horizontal plane. So it's got no acceleration in the vertical direction, which means that the vertical component of the resultant force is 0. Well, that's clear. The resultant force is in the horizontal plane. So we could look at the vertical components of these three vectors, sum them, and we get 0. So what's the vertical component of vector n? Well, that's just vector n itself. What's the vertical component of vector 3g? Well, that's just vector 3g itself. Now what about the vertical component of vector t? Well, we could just project the tip of t across here to the vertical. Now I've actually drawn this incorrectly. The tip of vector n is not actually here. We'll soon see a more realistic picture of the setup. But okay, we would project across here and try to get the length of this line here. That's 30 times cos alpha, because it's the side adjacent to alpha. So it's the vector 30 cos alpha. It's this vector here. Now, this is a vector equation, of course. It sums to 0, get the 0 vector. But let's look at magnitudes. So let's just take upwards direction. So we take the magnitude of vector n, that's n without the arrow, plus the magnitude of the vertical component of t, since they're both pointing upwards. The vertical component of t, as we saw, is 30 cos alpha. So these components are pointing in the same direction, upwards. And then we take downwards. Well, there's only one vector with a downward vertical component, that's 3g. The vertical component is the vector itself. So these must equal. Okay, so we need to get cos of alpha. So we can go up to this right angle triangle that contains angle alpha. The cos of alpha is adjacent to alpha, which is 3, divided by the hypotenuse 5. Okay, if you plug 9.81 in for g, you will get 11.43 newtons. Here is a slightly more accurate picture of the setup. You see, we want the vertical components of these two vectors to sum to a value that's equal to the magnitude of this vector. So we want the length of this vector here plus the vertical component of t, which is this here. So when we add the magnitudes of these two vectors, we want to get the weight vector. So this is probably a slightly more realistic picture.